If you go on Amazon or walk into an appliance store right now, you will see a sea of black glass. It's modern, it's sleek, and it's incredibly confusing. On the left, I have a stove that uses space-age magnetic fields to cook food without getting hot. On the right, I have a stove that uses a light bulb to blast your food with radiation. One is called induction. The other is called infrared, or sometimes just radiant ceramic. They look the same. They both plug into the wall. They both have touchscreens. But if you buy the wrong one, you might end up with a stove that hates your pots, or a kitchen that feels like a sauna. Today, we are going to tear apart the marketing and look at the physics. We are going to explain exactly how these two technologies fight the laws of thermodynamics. We will cover the speed, the safety, the efficiency, and yes, the weird science of why one of these might melt your plastic spatula, while the other one won't even warm it up. By the end of this video, you won't just know which one to buy. You'll know exactly what is happening under that black glass every time you make dinner. First, let's address the elephant in the room. Why do they look identical? Both systems use a top layer made of glass ceramic, usually a brand like Schott Ceran. This isn't normal glass. It has a very low coefficient of thermal expansion. That's just fancy physics. Talk meaning, you can get it screaming hot and then splash ice water on it, and it won't shatter. But what lies beneath that glass is what separates the past from the future. If you turn on the infrared stove, you see a bright red glow instantly. It looks like the eye of Sauron staring back at you. If you turn on the induction stove, you see nothing. No light, no glow, maybe a quiet hum. This brings us to our first physics lesson, the mechanism of heat generation. Let's start with the infrared stove. Despite the futuristic name, this is actually old-school technology wrapped in a new package. It is technically a type of electric-resistant stove. How it works. Inside the casing, usually coiled in a circle, is a ribbon of metal alloy, often nichrome, or a set of halogen bulbs filled with gas. When you send electricity through that ribbon, it fights the flow of electrons. That struggle creates friction, and that friction creates heat. But unlike the old gray coil stoves from the 1980s, these elements are designed to emit a massive amount of infrared radiation. The physics, think of the sun. The sun warms the Earth through the vacuum of space using light waves. You don't need to touch the sun to feel it. That is what this stove is doing. It is a miniature sun. 1. The element glows red hot, up to 1200 degrees Fahrenheit. 2. It shoots infrared light waves straight up. 3. These waves hit the ceramic glass. 4. The glass absorbs the energy and gets hot. 5. The hot glass touches your pot. Conduction. 6. The pot heats your food. The middleman. Problem. Notice how many steps that took? The element heats the air inside the box, which heats the glass, which heats the pot. This is a thermodynamic chain, and at every link in that chain, you lose energy. The glass acts as a massive thermal battery. It holds on to heat. This is why, even after you turn an infrared stove off, the hot surface light stays on for 20 minutes. The physics of the machine demands that the glass itself becomes the heat source. Now, let's look at induction. This is where things get weird. Induction does not generate heat. I repeat, the stove does not generate heat. It generates magnetism. How it works. Under this glass, there is a coil of copper wire. When we turn it on, we send an alternating current, AC, through that coil. This creates a rapidly oscillating magnetic field above the glass. We're talking about a magnetic field that flips north-south, north-south, about 20,000 to 50,000 times per second. The physics, if you put your hand in this field, nothing happens. Your hand is not magnetic. But if you place a pan made of a magnetic material, like iron or steel, into this field, two things happen instantly. 1. Eddy currents. The changing magnetic field pushes the electrons inside the pan's metal. They try to flow in loops, eddies. But the metal isn't a perfect conductor. It resists this flow. This internal friction generates heat instantly inside the metal. 2. Hysteresis. The magnetic flip. The magnetic domains inside the iron are being forced to flip back and forth 50,000 times a second. This molecular vibration creates even more heat. The result, the stove stays cool. The glass stays cool. The pan becomes the heater. We have eliminated the middleman. We aren't heating the glass to heat the pot. We are transferring energy directly from the grid into the molecules of the cookware. Part 4. The speed and efficiency battle. Physics is cool, but I know what you're asking. Which one gets dinner on the table faster? Let's look at the energy transfer efficiency. Infrared efficiency, 60 to 70%. Because infrared relies on radiant heat, it sends heat in all directions. Yes, reflectors push most of it up, but a lot of it escapes sideways. It heats the air in your kitchen. It heats the glass. If you boil water on an infrared stove, you're wasting about 30 to 40 cents of every dollar just heating your kitchen. Induction efficiency, 90 to 95%. Because the energy transfer is magnetic, the air doesn't steal it. The glass doesn't steal it. Almost 100% of the energy goes directly into the food. The boil test. Reality. If you take 1 liter of water, gas, 7 to 8 minutes. Infrared, 5 to 6 minutes. Induction is so fast that it actually changes how you cook. You can't put the onions on and chop the garlic. By the time you turn around, the onions will be burning. It is faster than a microwave for liquids. So far, induction sounds perfect, right? It's fast, it's efficient, it's magic. But here is the catch. The Achilles heel. The reason many people return their induction stoves the next day. It is incredibly picky. The infrared advantage. Universality. Physics doesn't care what you put on an infrared stove. Heat is heat. Do you have a clay pot for traditional curries? Infrared works. Do you have cheap aluminum non-stick pans? Infrared works. Do you have those glass visionware pots from the 90s? Infrared works. Do you want to roast a papa directly on the burner? Infrared works. Because the glass gets hot, anything that touches it gets hot. It is the universal soldier of cooking. The induction constraint. Induction relies on ferromagnetism. If the pot isn't magnetic, the field passes right through it like a ghost. Aluminum? Fail. Copper? Fail. Glass ceramic? Fail. The magnet test. Before you buy induction, go to your kitchen with a fridge magnet. Stick it to the bottom of your favorite pots. If it sticks firmly, you are safe. If it falls off, you have to buy new pots. There is a workaround. You can buy a steel induction interface disc that sits on the stove, but that defeats the whole purpose. It turns your sleek induction stove back into a slow, inefficient hot plate. Now let's talk about the danger level. This is where the physics of thermal inertia comes in. Infrared danger. An infrared stove is essentially a flat iron. When you turn it off, the glass is still 700 degrees Fahrenheit or 370 degrees Celsius. It takes a long time to cool down. If you spill sugary sauce, like a teriyaki or jam, on an infrared stove while it's hot, the sugar will caramelize and fuse to the glass instantly. It is a nightmare to clean. You basically have to scrape it off with a razor blade. Induction safety. When you lift the pan off an induction stove, the energy transfer stops instantly. Yes, the glass is warm because the hot pan was sitting on it, but it's not generating heat anymore. The paper test. You can literally place a paper towel between the pan and the stove to catch splatter. The magnetic field shoots through the paper, heats the pan, cooks the food, and the paper does not burn. Disclaimer. Don't do this at high temps for long periods, or the heat from the pan might eventually scorch the paper. But it proves the point. The stove isn't hot, the pan is. Cleaning is a breeze because food doesn't burn onto the cool glass. You just wipe it away. I see this comment on every video. I don't want induction because of the radiation. Let's clear this up with physics. Infrared radiation. This is thermal radiation. It is heat. It is the same stuff coming off a bonfire or a radiator. It is harmless unless you touch it and get burned. Induction. EMF. Induction uses non-ionizing, low-frequency radiation. It is similar to the radio waves that pass through you every day. Unless you have a pacemaker, in which case, consult your doctor, as strong magnets can interfere with electronics. Induction is perfectly safe. It creates a localized magnetic field that drops off to almost zero, just a few inches away from the burner. You are getting more radiation, holding your phone to your ear, than you are cooking eggs on induction. So, we have looked at the magnets, the lights, and the heat. Which one belongs in your kitchen? Buy the infrared stove. If you are a traditionalist, you cook with clay pots, glass, or specific non-magnetic traditional cookware that you refuse to replace. You are budget conscious. Generally, infrared units are 20 to 30% cheaper than induction. You want roasting ability. You want to char peppers or toast breads directly on the hot surface. Buy the induction stove if you value time. You want water to boil in seconds, not minutes. You want precision. You want to melt chocolate without burning it. Induction can hold very low temps perfectly. You hate cleaning. You want a stove that you can wipe clean with a damp cloth immediately after cooking. You care about AC bills. It keeps the kitchen significantly cooler in the summer. The infrared stove is the past. It's reliable, simple, hot. The induction stove is the future. It's fast, precise, cool. Personally, once you experience the speed of magnets, it's really hard to go back to waiting for a light bulb to get hot. I'm Sal, and that is the physics of your kitchen.